Good. Hello, everybody. I'm going to be just talking about a library I've been working on for a while called Spire. Basically, Spire started as a project between me and another longtime Scala developer, Eric Hassan. Basically, neither of us were really happy with what was provided by default in Scala as far as numbers and abstractions over numbers. So he was sort of coming at it from the side where he was doing big or large-scale rasterization sort of things, and you need a lot of speed. And he couldn't get, and he also needed to be abstract. And he couldn't get that with what Scala offered. On the other hand, I was in grad school at the time, and my big problem was really, that the standard number types aren't very accurate, and I was hitting a lot of issues. I needed to use some exact number types, and the abstractions Scala provided by default were just not specifying exactly what I needed. So we kind of got together and we decided to make a library that solved both our problems. So, worked with abstract number types, had, higher precision number types as well, and would still retain the speed of just working with like primitive doubles and ints and that kind of stuff. So in particular, I'm just going to give a quick overview. So I'm just going to start by going over some of the Spire new number types that Spire offers, and exactly what those are. They got a kind of list there. And then I'm just going to kind of give a brief intro to how we treat abstract algebra in Spire, and some examples that hopefully convince you that being abstract about your number types is quite often a good thing. You don't always have to do it, obviously, but there's many use cases for it. So throughout this talk, we can just assume that I've imported these three things at least. So basically, math contains all our data types, so it contains our numbers. That we add in a bunch of utility functions as well, like sine and cosine and whatnot. Algebra contains all our type classes, so whenever you see me using a type class, this probably comes from algebra. And we also have our implicits. This just brings in all of our implicits. You can also do it piecemeal if you don't want to clutter up your namespace with a ton of implicits. But this brings in all the operators I use, like plus and minus. But it also lets us use literals for constructing some of our numbers. So let's start with exact numbers because I like them and they're fun. So basically, sometimes we hit a point where we just want to stop worrying about errors and we just want to deal with exact number types. So Scala provides basically really just one. It has BigInt. You have your integers. Whenever I talk about exact number types here, this is always you can assume that we are constrained by the memory in the machine, so therefore it is not truly exact. But for all intents and purposes, it's exact. Big decimal sort of exactly represents decimal numbers. But I mean, we're more concerned about how you would use them when you approach like a paper that's talking about an algorithm that just assumes that all math is always correct. So BigInt, Spire tries to fill in the gaps. So safe-long is kind of an alternative to BigInt. I'll talk about it a bit. But the three new types are really rational, algebraic, and real, which as you can imagine, kind of cover the rational types, algebraic types, and real types. Yeah. So basically, BigInt, as Scala provided, is pretty much big integer. It just wraps it. Doesn't add all the methods back in for some reason, so you don't get things like its probable prime. But it is an arbitrary precision integer type. So it is exact for addition and multiplication. You can get very far with integers, I feel this is necessary to say, because if you're dealing with, from my perspective, when you're implementing a lot of algorithms, even if they're working with rational arithmetic or doubles like that, you can quite often turn this into a problem with integers and just kind of carry a scale along with it. It's usually a slower approach, but it works. So Spire we came along, we provided the safe long. Our main problem was BigInt was great, but we wanted to get something that was a little bit faster for the common case where you really do have small integers. So safe long basically just has two types. It'll either wrap along or wrap BigInt. So basically, as long as you're under 64 bits, it'll use long arithmetic. I think somebody's mentioned before that the IBM JVM does this as well, so I've never actually benchmarked against that IBM JVM, but this is faster than just using BigInt by itself if you're really concerned about that stuff. The other thing it provides is rationals. Rationals are great. So basically, it's like a big integer, except you can add in division, so you can divide anything. But the important thing is that as far as it has a canonical representation. So how we actually represent the number is exact. And so you can always look at it and see that number, which will make more sense later on when I show you algebraic and real. So when I talk about canonical, you can see here, whenever you construct one, it will always turn into a canonical form. In this case, the numerator and denominator are co-prime, so they have no common factors, like as you know your rationals to be. And more importantly, the denominator is always positive, blah, blah, blah. You can also see Spire provides nice little literals you can use. So you can just use the student interpolation, but it'll, at compile time, it'll parse that into a rational, which is nice. And as I said, they are big. You can get very big rationals. Rationals tend to blow up quite fast. Much like safe-long, or rational implementation does try to keep everything in a long if it can. I don't have the benchmarks with me here, but basically everything below 64 bits is quite a bit faster. Once you get past that limit, it starts getting slower. But if you are using rational, you're using exact types, and you get to a point where you want to make things kind of small again because you're worried about your memory usage or something, you can always limit the size of the numbers. So this is the type that it's quite nifty as well. Algebraic basically lets you represent arbitrary algebraic numbers. So for your math class, you might remember the algebraic numbers are basically just roots of a rational polynomial. So basically what that means for us is that, like rational, we can perform addition, multiplication, that kind of stuff in division exactly, but it also throws n roots into the equation. So we can do square roots and cube roots and roots of rational polynomials. So what that means is, like, actually I'll show you in a second. But the key here is that we do not have a canonical representation for algebraic. It's not like rational in that we're always having this nice little form that's exact. Instead, we always just record the operations as they go. And what we can then do is we can approximate the number to any desired precision, and we can also use a special property of algebraic numbers that lets us always know what the exact sign is. So why I say it's important is, like, so for instance, we have, in this case here, we have our function that basically just takes a number and returns the square root of it. So when we say val x equals f2 here, we're not actually evaluating the square root of any number, or the square root of 2. What we're actually doing is just recording the fact that you've taken the square root of 2. So when you actually then try to convert it to a big decimal and you say, well, you want decimal 64, it'll evaluate it to your desired precision. If you then try to, ask for it again with a higher precision, it'll do that again. It doesn't really care. It just always does it whenever you ask it to. But the other thing it does provide is exact sign tests. For a lot of combinatorial algorithms where, like, not so much when you're dealing with numerical precision, but more like, things like sign tests, so what side of a line a point lies on or something like that. You really care about what the sign is, and having exact sign test is very important. So you kind of have these two numbers here. We get this crazy expression you can see here. And it may not be immediately obvious, but that is 0. And we know it's 0 because algebraic guarantees its sign and says it's 0. That's very important. Another number type we provide, which loses the exact sign tests, is real. So real is really cool. It's exact. It lets you do n roots like algebraic does, but it also throws in log sign. You can do powers to, like, arbitrary other reals. Much like algebraic, you can approximate it to any desired precision. So for instance here, we're just taking the sign of real.e, and we can ask for a rational with 64 bits of precision or 128 bits of precision, and it'll just gladly spit that out for you. The problem is that we never really know exactly we can never really know what the full number looks like. So reals use something called a bit stream. So basically what it is you can always ask for any precision. It'll always give it to you. It'll spit out this bit stream of bits that represent the number. But you never know what you're going to see in the future. So in this case, we do the exact same expression we did for algebraic, and it tells us it's 0, but it doesn't actually know it's 0. It's just computing it to, like, 128 bits, and it's saying, well, it's still 0, so I'll say it's 0. But it doesn't actually know it's 0. There could be a 1 after, like, the millionth digit. We don't know. But they are really cool. They definitely are a nice way to look at things. The other thing Spire provides is unsigned integers. So for when you just need that extra bit, you really don't care about negative numbers. So the problem is that basically, as it stands right now, the JVM doesn't have unsigned integers. So therefore, Java and Scala don't bother trying to implement it either, because I guess they didn't want people using them and seeing performance issues or something. I'm not entirely sure. But the main thing that led to is basically that all Java and Scala code everywhere has tons of runtime checks for things like, if you have a vector type and array type and you're trying to get a value out, it's not enough to make sure that it's below the size of your array or vector. You also have to make sure it's not below 0, because -2 would, is completely valid value that somebody may pass you and you don't know. It's not that bad, but I mean, why not just use types? So Spire provides standard unsigned types you might expect. So byte shorts, ints, and longs. Natural is there as well. It's kind of like an unsigned BigInt. It's implemented in a slightly different way. I don't know if a lot of people use it or not. But obviously, yeah, so if you just use unsigned types, you don't have to actually sit there and do a runtime check that just could be a compile time thing that you never have to worry about. An important thing here is all the unsigned types are just value classes. So if you're worried about performance, you're just basically operating on the signed versions of them. They basically behave as you expect with like overflow and everything. Everything from int and below is very fast because we just widen and operate like either with an int or a long. Ulong, basically the only thing that's going to really be slow is division, because division is always weird. But I mean, they're fast types. There's really not a lot to them. And I think it's kind of one of the classic examples for value classes. So if you ever need unsigned types, they're there. There's also a ton more stuff in Spire. I'm just going to kind of whip through a few things. So we have complex. Complex is parameterized on the type. We don't care if you want. You can have a complex of double. You can have a complex of int. So here you can see I'm using my real, my imaginary to just int. It lets me do that, because why not? Another thing that's really cool here, if you remember your math class, got Euler's identity at the bottom here. So basically, because it doesn't care about the type, we can say, well, we want a complex of reals. And as we know, reals are exact types that represent any real number. And so basically, when we use Euler's identity, we actually get the correct answer, which is that it's 0. It'll always tell you it's 0. I mean, it doesn't know it's 0. But you always get 0 because we know it's 0, which is definitely a very cool property. So we also have intervals. I think intervals are something that everybody always needs at some point in their life. And this is a fairly robust implementation of them. And you can do open or close on any side you want, points, empty intervals, everything else, and you can do all your arithmetic on them, and unions and everything else. So if you're in need of intervals, they're there. There's a whole bunch more polynomials. I'm going to be giving a talk on FP filter at any Scala. It's definitely a cool type that I like because I made it. There's a whole bunch of other things which I'm not going to probably get into at all. But yeah, there's a whole other side of Spire, which is that's kind of the number types. We tried to add these number types we thought were missing from Scala and were kind of key. So those were like our exact types and our unsigned types, and then a few others that we kind of threw in there. But a whole other side of this is dealing with these types in an abstract way. So basically, abstract algebra is all about just saying, well, we don't care if it's a double, we don't care if it's an int, we don't care whatever. What we want to focus on is the operators available to us and their properties. And so what we do is we just say take the doubles and we try to generalize it and figure out what we actually need from it. So as a simple example, there's the semigroup. The semigroup is one of the simplest sort of abstract algebra structures you can imagine. It's a single binary operator and a single property. So we have some type A, and we have a function basically from A to, that takes two A's and returns an A. And the only property is that it has to be associative. We'll see why this is a very good thing to encode, even rather than just using a straight function. But obviously, semigroups, an associative binary operation. It generalizes addition, generalizes multiplication, concatenation, whether that's list or string or map or whatever else. If you have options or else, that's just a semigroup. And the takeaway is kind of like, a lot of your binary operations are associative. And so it's an important sort of property to convey in your code. So how we would encode a semigroup in Spire is we basically say, we encode the structure as a type class. If you don't know what type classes are in Scala, I'm not going to be able to tell you too much about them, but I'd suggest you do a Google because they're fantastic. But basically, we just say that we have a trait that's a semigroup, it takes type A, and we just encode the operator as literally a method on the trait. You can see here we have a little SP. I just put that there so that people are aware that all of our type classes in Spire are specialized. And if that's important to you and you know what that is, then that might be important. So we encode the operators just as implicit classes. I mean, not really actually using implicit class, but for all intents and purposes, we are. I kind of put this up here because you can just see here, adding that operator is really straightforward, but we actually do use macros in Spire for all of our operators. And what we do with these macros is every time you say x plus y, Scala by default uses implicit classes will actually turn that into an object allocation that wraps it in a semigroup lots class and then calls the plus method. We can get around this a bit with value classes for some cases, but not for a lot of the ones in Spire. But what the macro does is it just provides a very generic way where we just remove that allocation and we just call the binary operator on the type class directly. So that avoids, that's just a performance enhancement. So if you're ever using this, you don't have to feel guilty for all these object allocations you're adding. They're not there. We then encode laws as property tests. Property tests are another thing where if you don't know much about it, I definitely suggest looking it up because they're great. But the key thing here is all you're saying is that if you give me any 3 A's, this thing will always return true, whatever I put here. So this expression, we're encoding the associative property in code. We're just saying, so we're just saying a function that takes any 3 A's, it'll do this. Scala check is a great library, and what it'll do is it'll generate a bunch of random A's and throw this into it and always verify if it's true. And it'll do this like 1,000 times, 10,000 times, however much you want. And if it ever comes back false, then your test fails. So obviously it's not like in a mathematical sense you've proved it's true, but like from a practical sense, you've tested this with a whole bunch of data that you could not have just done otherwise with a simple unit test. It also lets us abstract this and say that anybody who has a semigroup can call this, and they will get that. We'll be able to verify that their property is actually there. So, bigger question is why would you actually use this? So, my main sort of ideas, or my main viewpoint is that first it frees you for your implementation. And why that is because it makes your requirements clear by using a more precise type. And actually asking for what kind of properties and operators you want, it frees your implementation, but maybe restricts your users in some way. It's kind of that whole freedom is slavery thing, right? The other thing is it frees your users. So instead of the main thing here is if you just ask for what you need, so you're not saying I want a double anymore. You're saying I want a field. Don't worry about what a field is. Then what it means is the user doesn't have to always provide doubles now or make sure the data is a double. It can give you a big decimal. It can give you a rational, whatever they want. And the code will still work. So I'm just going to kind of give some examples for what I'm talking about when I say make your requirements clear. So we're just going to show 2 sort of implementations of reducers. And when I say reducer, I mean literally just like Scala's reduce method on their collections. So the first one's just going to use a binary function. So we're not saying if there's any properties associated with it anymore. We're just saying give me a function that takes 2 A's and gives me an A, and a sequence, and I will spit you out an A. So I tried to kind of write this here. It's kind of terrible, but basically, we're just saying that we're going to apply f to the first 2, then take the result of that and apply to the next one. We're going to end up with a single value at the end. The second option is we can do this with a semigroup instead. So instead of asking for a function that takes 2 A's and returns an A, we say, well, I want a semigroup. So we're no longer saying give me any function. We're saying give me a function whose operation is associative. And this is a very important distinction, which I'll make clear in a second. So if we have the kind of simple case here where we just implement it by literally calling reduce on the collection, this works fine. Same thing with the semigroup. We're just using the operator, and this will work fine. We can call it on. We have a simple example here: 1, 2, 3, 4. We just want to add them all up. It works. The second one, we don't actually need to provide the operation because there's an implicit one available. That's great. The problem is what happens when we want to actually start messing with the implementation. So we're like, this is kind of slow. I actually want to make use of 2 cores. Obviously, this is not the greatest thing in the world, but basically, in the first case, when we have a function, all we're going to do is we're going to take whatever sequence they give us, we're going to split it in 2, and we're going to throw the 2 results in 2 threads and execute it. Or reduce each one by itself, so we'll end up with 2 A's, and then we're just going to apply the function to the final result that's returned. There's actually supposed to be a final reduce there that calls that. I just forgot it in both slides, so don't worry about that. Anyways, this is the same code with using semigroup instead. So you can see here, basically, we're just doing the same thing, except we're using the plus operator. And we're just awaiting the result for however long it takes to finish. But the key here is that when we give our same example we gave before, everything's hunky-dory. But the problem is that the first reducer didn't specify that the operation has to be associative. It just said give me any function. So what if I pass it subtraction? It's now violated its sort of doc string, right? The document said that I'm just going to give you the equivalent of applying them in sequence like this. And that's actually no longer true because we tried to get smart with the implementation. So the reason why it's nice when we use a semigroup instead is that we're telling the user up front that in a very honest way that your operation has to be associative, and if it's associative, then I'll return you the result. What that means is that we're free to then mess with the implementation within the constraints of the type class we use, the semigroup or within the semigroup. So I just want to finish this off. There's a great library out there called Algebird by Twitter. So they are focused on big data analytics, and they have built a great library all around semigroups and monoids. Monoids are just like semigroups, except we've added an identity element. So for addition, this would be 0, for instance. For multiplication, would be 1. And so what they realize is that almost all the reductions they were trying to do, from in MapReduce and everything, were just semigroups or monoids. And so therefore, instead of actually just letting people do whatever, if they take monoids, they can optimize that a little better. But the main thing here is that there's a lot of stuff that are monoids, and you can take a look. They got a lot of really cool stuff for doing big data analytics if you're into that. The other thing, of course, is that by using these things, you don't tie your user to a data type. So if you abstract over your number type, instead of trying to nail down oh, I want to use doubles, or no, I want to use big decimals, you can just say, I don't really care, actually. Just give me whatever the heck you want. I'll try to do what I can. And so obviously this is a big problem actually with computers. Spire for their default stuff. Scala and just throw 50 more new data types that provide much the same things, like plus, addition, division, that kind of stuff. 15 of these things alone are just subsets of the reals, like int and real and algebraic and rational and that kind of stuff. And so choosing any one specific number type is really limiting you. You're basically telling the user they can't use 14 other things that are available to them. And so we can abstract over numbers. And so I'm not going to get too much into the type classes themselves or the algebraic structures, just because there's a lot there and there's not nearly enough time. But suffice it to say that there's at a very basic level, these things called rings. We have a bunch of different variations that provide slightly different operators and properties. And but the main thing is that they basically are just generalizing over the notion of addition and multiplication and how those distribute over each other, and then just throwing some random stuff in there depending on what. Then there's also fields, which just throw division into it. So it's saying we don't have just addition and multiplication, but we can also divide things, and the result of that will live in the same type. So integers don't really have division, because if you divide something and multiply it by, again, you violated one of the properties, which is that those things live in the exact result lives, I guess, in the type. We also have type classes for all sorts of other things you want to do. The main thing is I'm just going to say that generally, if you're going to use a double, just think twice, because they're generally not great at standing in for integers. People would rather just use integers, and that's great. So going from that, big decimals are great actually, because people work with decimal. When you write in your source code, you're actually entering decimal numbers for doubles, and it's that conversion that kind of throws people off sometimes. They don't realize that there's actually a binary number underneath, and that's going to mess with you. And so there's much better things out there. But another thing is if you've ever implemented, coming from grad school, if you ever look at a lot of algorithms, they all just quite often will just make this blanket assumption that your math is correct always. If you they don't worry about overflows, they don't worry about this kind of stuff. It's really frustrating when you try to implement these things and things don't work because you had an integer overflow or your doubles were slightly incorrect or whatever, And so, using doubles, you basically have built those inaccuracies into your implementation, which is frustrating. So here's an example where, we're just adding a method mean. It'll take any sequence of doubles and will let us take the average. I know this is not a great implementation for doubles for average. I've been told this before. I know about the incremental one, but this is just a slide, so let's go with it. Anyway, so if we instead just say, we don't actually care about that, what we need is we need a number that we can sum and then divide another value from, then what we actually just say is we don't want a double, we want a field. A field, if you remember, basically just says that we have addition, multiplication, and division. And so basically, we can actually re-implement mean, just talk in a generic way, just with these operators and the properties that they have. And so this kind of more fulfills the actual, a lot of the reasons why people went to Java many, many, many years ago, at least the marketing from Oracle, or not Oracle, like a Sun. But you write this once, and then you can run it with anything. It doesn't really matter. Rationals and doubles, for all intents and purposes, they do the same thing. So why not just let your user do that? And so that brings us to the next point, which is that asking for what you need, you enable choice. So that's important because if you look at a lot of Java libraries that have polynomials and stuff, they fix you at double, and you only have doubles. But quite often maybe you want exact rationals, or exact polynomials. We don't use rational or something like that. So you can see here we just construct some polynomials that are parameterized on rational. You have operators like multiplication. That's great. Another cool one is we can say find the greatest common divisor of the two polynomials, and we find the term that's common in both. And that's all. That GCD algorithm is just using Euclid's algorithm. It's generic, so we can just call Euclid with two polynomials, and we get a result. It's great. We can also say, okay, well, we want integers instead. That's fine. You can have polynomials with integer coefficients. Everything works up until the point where you try to do something that isn't supported by integers. So GCD requires that in order to do Euclid's algorithm, you need to be able to do, your truncated division sort of operator that you're so used to with integers, where you take 1 divided by 2 is 0, of course, or 5 divided by 2 is 2. So you need to have that kind of operator available, and that's only available for a polynomial whose coefficients are rational. So, or more importantly, coefficients have a field available to them. And so we kind of get this error, you're not actually allowed to call it. But, so there's another library here which I sort of have worked on for my company that I work for called Freemium. And Freemium is focused on basically doing ad hoc and in-memory, small data, not big data stuff, manipulation and analytics for heterogeneous data. So if you've used something like Saddle before, it's kind of like that, except we don't tie you to a single type. So basically, you can imagine this being kind of like a CSV where you just have some data, and you can extract out the data as different types. But basically, we use Spire, and we abstract over all the numeric operations because we don't really care. And Implicit, we don't want to use doubles. We use big decimals a lot, and another number type called number in Spire. And so, I mean, by abstracting the numbers, we can do that, and if somebody wants to then use doubles, they can use doubles, and with Freemium, they'll get the performance of doubles, which is great. We don't have to make that choice for them; they can make that choice. There's a lot more type classes available. I'm not going to even go into these at all, but basically, there's a guy recently has come by and done a lot of great work on groups and group actions and that kind of stuff. And we also have abstractions for vector spaces and lattices, if you know what those are. I don't really know much about them, but it's interesting stuff. This is almost wrapped up. I'm just going to go over a few more things. If the abstract algebra stuff piqued your interest at all, there's a new project called ALGEBRA. It's basically a collaboration between Algebird and Spire. So as I say, there's me and Eric and Oscar Boykin from Twitter and Avi from who's at Stripe now, I think, are basically getting together and trying to take out the common bits between Algebird and Spire and put them into a single package with just the type classes. And it's a pretty new library, and there's a lot of stuff going on, and so if you want to kind of get into that, you might want to check it out and comment on some issues or submit some code or whatever. The next thing, of course, is I work for a company called Implicit Analytics. We're pretty much always hiring. There's only 2 of us in Canada right now. If there is more, that'd be great, so we can kind of start giving the New York office and a run for its money. But if you're all interested, you can hit the page, you can see what we do. It's a Scala shop, so I mean, there will be Scala. Yeah, thanks. Any questions?
So it's used a lot of like scientific computation, the computing.
Yeah, I'd say like he's asking a lot. He uses a lot of scientific computation. I'd say like when I think of scientific computation more as like a lot of people. I don't want. So the one thing that we don't do really is linear algebra. I'd say like we're not trying to take on. Actually, there's a guy who's working on a whole bunch of stuff for doing linear algebra stuff, but it hasn't been merged yet, and I think it's a little ways off from that. But we're not trying to compete with that. I'd say we really are. Spire is definitely more focused on things that are like real numbers and abstractions around those mostly. Does that make sense?
So what problem you're solving using this kind of package?
Yeah, so like in Freemium, for instance, it's basically this library for working with heterogeneous data. And so the main thing is that we kind of treat numbers uniformly within it. And so that means that if you're working with, say, like a column, right? So you have some column of, a series of data, I'll say. We have like, so you have a time series, like that has time and some numbers. We don't actually care what divides the numbers. So we try to treat them uniformly so you can get them out as doubles, you can get them out as big decimals, you can get them out as rationals, whatever you want, right? And all the operations you would expect to be available to you for, like, say, a series of doubles is also available for any operations. So in our line of work, we're representing a lot of currency information, and so we don't want to sit there and use doubles because we're going to lose precision. We'd rather use big decimals because that way we can do a lot of operations and not lose that. If somebody does division, whatever, that's fair game. But if somebody's just like summing, I don't know, two kind of fundamental values from like a balance sheet or whatever, right? We don't want to like lose some sense there because we're using doubles. And so we work with big decimals. But on the other hand, we also don't want to, for the analytics side of things, like if we're going to, get a series, we want to like say get something simple like the standard deviation. I'm not going to do that with big decimals. I want to work it out with doubles and do it with doubles. But I can do it with big decimals. But by using the abstractions available instead of working with just doubles, I'm allowed. I don't have to worry about that. I can work with the number types as I want to, so as big decimals, or as doubles, or as rationals, or whatever else.
I have two questions at that point. First is for the numerical side of the library, what are you using or what do you use to check the algorithms? Right? Check it against mathematics.
Depends which algorithm, but yeah, Mathematica is fantastic. I'm not ashamed to say that I quite often use Mathematica to check my work. But I mean, the great thing about doing this kind of stuff is that a lot of these things have really easy property tests to write. Like, I mean, if you're, for something like algebraic, there's like, kind of classes of functions that, are quite often zeros and stuff like that. And so I can quite often just run those through and, generate hundreds of test cases and for me, and I'll kind of verify it. I don't have to worry about that. But I mean, I'm sure there's bugs too.
And the second question we had was passive. There are people who are big advocates for type classes and APIs.
Sorry, for pardon?
Type classes and APIs, like for simple and
yeah.
non-like. And the big argument is that really hurts API because you guys force the types everywhere that we can't understand. So it's like math on the list versus set math for a function.
Yeah.
So you find that have the same problem types.
Yeah, definitely. I'd say like all this stuff is always the fundamental problem. I mean, like when I made Spire, when Eric made Spire, was that we were both trying to solve our own problems. I was trying to solve it in Java and Python, all this stuff, and I was hitting these roadblocks. And eventually we got to this point, and I looked at Scala, and I realized that they had these features that solved my problem, like type classes and stuff. And I was like, this is fantastic. This is exactly what I need. So on the one hand, like that solved my problem, but I had to put some work in to finally get to the point where I realized that this is solving my problem. And I feel like a beginner, when they see this, it is complicated, and it's not always like there's just a lot of types, and at some point you just gotta be like, this is nuts. I don't want to learn this. And I don't blame anybody for doing that. So there's definitely a learning curve. But I definitely will say that, like, yeah, it's like a lot of these things. So yeah, same thing with Haskell, right? It's like, these people have gotten to a certain point where they hit problems, and these things have solved the problems, and so they use them, and it hurts beginners. I don't know if there's a great way to really fix that. I don't know. Maybe there is, but yeah, there's always going to be that kind of like ramp up, especially with a library like Spire, where we have kind of expect people to do a little bit of reading, I guess.
Can you explain the difference between saddle and algebra? Once you roll
Saddle and freemium?
and algebra, the new one. Your algebra is combining both Spire and algebra.
Oh, Algebird, yeah.
So can you explain the difference between saddle and
I don't know if Saddle would be great. So Saddle more competes with like framing. It kind of provides like the ad hoc data manipulation. Our main use case when we hit it was that we're trying to work with heterogeneous data, and Saddle always encodes the type of the values of your like frame like data, right? In there. So you can have like a frame of doubles, you can have a frame of strings, but you can't have like a frame of strings and doubles that are mixed. So that's kind of why framing was built, was like, okay, well, let's remove this assumption that we always have a type for the values. What can we do? I'd say that algebra, on the other hand, is just literally taking like the abstract algebra, the type classes I talked about with Spire. The same thing, if you look at Algebird from Twitter, like they have like the same kind of type classes, and we're just kind of like, this is insane that we're duplicating these things. They're focused on big data, and we're kind of focused more on like real numbers and that kind of stuff. And so we were just kind of seeing like, well, let's make a new library that has both, and that way we can both depend on it, and we're not cluttering the ecosystem with two implementations of the same thing.
Maybe one more question. We can wrap it up. Do you plan on sticking around a little bit after?
For a little bit, I gotta probably get home pretty fast,
Okay.
but
Just for interest of everyone else's time.
yeah. Cool.
One more question.
Yeah, or no?
Well, I was going to say, are there anything in the built-in Scala types that the built-in Scala numeric types have that Spire doesn't? Is Spire like a drop-in for numeric types?
So we work with the Scala types, right? So like the great thing about this is like Spire also. I mean, if you're using big decimals, for instance, and you're using Spire, then you can do sine, log, cosine, square roots of big decimals, which you can't do because big decimals isn't provided by default. So if you're interested in that stuff, Spire provides this. We don't try to compete with like the number types they provide. We're just trying to like add on the ones that we think are missing. Like I said, I use big decimal a lot, so I mean it's all about what you need.
All right. Thanks for that presentation. It was fantastic.